And I should be live. Double check this. Okay, so preview is up and running. Can't tell about the volume because I think that's going out through the HDMI. But the microphone meter is looking appropriate. Let's go ahead and switch this to dark mode. And let's go on over to my GitHub for learning Rust. And we'll continue on with, I believe, chapter 14. Also, one thing, I just realized that I left the window open in here. So I'm going to get that closed. And then we'll get continuing on. All right, so we're currently at creating the second crate in the workplace. And I'm not... Oh, right, because we're in the middle of a do it section. Stacking, good morning. Here we go, time for some programming, boys. That's right. We all have a few more days until everybody doesn't wake up at 8 a.m. to just check to see what how the gigantic once every 4 years tournament goes. Is the World Cup every 4 years, or is it like every 6 years or 8 years? I don't actually remember. I haven't been paying attention to it. All right, so Dominus projects mine 4, you think? Okay. So I'll be able to do this for a while more before it happens again. Okay, so we're gonna go into add. So add is the name of our workspace, and then we have adder as a binary that we added in here. And we are American who cares about soccer. That's pretty much it, right? I am an American. I call it we call it soccer, although sometimes I do remember to call it football when talking to my European friends. There's actually a huge number of people in Denver who love their soccer, and so have been glued to the TV / monitors / watching it during work instead of doing work. I heard yesterday that a story of one programmer who puts it up on his big monitor and has been doing all of his coding on his notebook display because, well, what's more important? Clearly watching soccer. Okay, so enough about that. Let's do some Rust here. Creating a secondhand crate in the workspace. Next, let's create another member crate in a workspace and call it add1. Change the top level cargo toml to specify the add1 path in the members list. Here's a problem that I notice here. And they changed it earlier on, but it looks like they missed this in the documentation. So I think that I want to make a note of this somewhere. And I'm not sure exactly where. I didn't bring my phone down here with me, so I couldn't do anything about that. But maybe we could write it in my other display. I'll just write it to myself here, which is chapter 14. Actually, you know what? I could put it in here. In Learning Rust, chapter 14. So we have this. Let's come down. Let's vim the README. You haven't had your coffee and you zoned out. What happened? The big thing is I just realized that the command they're having us run is incorrect. So cargo new add-on does not create a binary, does not create a library, it creates a binary. And so that should be changed in the documentation. So documentation fixes for the book. Last time that we found this, there was already a pull request in, it had already been accepted, and it was just waiting to be fully merged in. So we'll see whether or not inside of creating a workspace, just do specifically, we want all of this. I guess I kind of maybe not want to do this, but for creating a library, need lib flag. The book has already been published. That sucks for the hardcover folks. Yeah, no, it definitely does. But at the very least, we can maybe help out with the digital copy and the next time that it goes to print. Okay, so the best thing is that the first time that they walk you through it earlier in a book, they do cover that. So I'm hoping that like by the time somebody gets here, they're gonna have exactly the same reaction that I did and say, that's wrong. I've already done it the other way, and that's how it works. And then they won't actually make the mistake. They'll just like move on. All right, so we're going to generate a new library crate called add-on. Going to save and close that. Let's move back in. CD add. We want to first create this add-on, so we're going to do cargo new -- lib. And what is this called? Add one. Compiling this new crate may not work due to invalid workspace configuration. Package believes it's in a workspace when it's not. Current. Okay. Interesting. This may be fixable by adding add one to the workspace.members. Oh, okay. So it's literally just telling me that I need to reverse the order that I do this in. That it wants me to do this first. Okay, that's actually interesting. Oh, let's do code dot. And in our cargo toml, we have adder, and now add one. That. All right. Your add directory should now have these directories and files, and I believe it does. In the add one source librs file, let's add an add one function. So public function add one takes an i32-bit integer, returns a 32-bit integer, and just adds one to it. Okay, sounds like something I can do here. So source librs. I don't know if we need our tests here. So we're gonna do pub function add. What do they end up calling this? Just add one. Add one. It takes an x, which is an i32. we are returning a I32, and we just are returning X. Okay, so that was pretty easy. Now that we have a library crate in the workspace, we can have the binary crate adder depend on the library crate add1. First, we'll need to add a path dependency on add1 to adder cargo.toml. So in dependencies in adder cargo.toml, okay, so that's going to be interesting. So let's go to adder cargo.toml. In dependencies, we want to say add1 equals, okay, so it's add1 equals, and then it's going to be this sort of curly bracket object syntax, but it's obviously very different. It's a toml type object. Path equals, and then where we're going. So I don't feel like this could have multiple things in it like that, which is path equals ... slash, and it's going to be add1. Okay. Cargo doesn't assume that crates in a workspace will depend on each other. So we need to be explicit about the dependency relationships between the crates. Next, let's use the add1 function from the add1 crate in the adder crate. Open the adder source main rs file and add an extern crate line at the top to bring the new add1 library crate into main scope. Then change the main function to call the add1 function as in listing 14.7. So extern crate add1, and then we can just use it. That. So inside of main rs, extern crate add1. Is it with the dashes? No, it's not. Add1. Did I do it wrong? I may have done this wrong. So add1 is with dashes here, and that kind of needs to be changed, doesn't it? So let's rename this to add1 like that. But of course I can't just do that. In its cargo toml, add1 needs to be an underscore. Main rs is good with that. And add1 in its cargo toml, change this here also to underscore. I don't think there's anything librs that we need to do for that. And we need to tell it about add1. All right, so let's where did main go? Here he goes. I feel like we're getting a little overwhelmed with toast messages here. Oh, geez. Yeah. I didn't even notice those. I was looking in the upper side part of the screen. Okay. So that's just like VS Code going crazy. You don't have an extension for toml. Are you sure you don't want me to download one? Please let me download one. I would really love to download one. All right. Next, use the add1 function from the add1 crate in the adder crate. Okay, so we're just going to go in and say, okay, we're extern crate, add1, and let num equals 10, and then we just add 1. So we'll come into main here, let num equals 10, and then we're just gonna call it, I guess. So print line original number is 10 after adding is, let's also not have this open. Okay, and so then in here, we're gonna have add one, double colon, add one. Now we pass it in num. All right. Let's build the workspace by running cargo build in the top level add directory. So here we are. So it's cargo build. Build to parse manifest. And this is the add adder cargo.toml caused by could not parse input as toml. I expected a table key, found a new, oh, so I can't use new lines there. Okay, so that's what the problem is. So I need to come back to adder cargo.toml, and this has to be a single line. No matching package name, add one. Did I? I missed one place. Okay, compiling. Print line, original number is, oh, I forgot to put in the two different things here. So in main RS, instead of, this first one needs to be and one more time. All right, so it finished compiling. Okay, so we built the directory. To run the binary crate from the add directory, we need to specify which package in the workspace we want to use using the -p argument and the package name with cargo run. So cargo run -p adder. So if we take a look at the names of our folders here, we have adder, so we could just do cargo run -p adder. Original number is 10, after adding is 11. Maybe if you had that helpful toml extension that VS Code tried to give you, would have been avoided. Yeah, you're probably right. They're just trying to be nice to me. Okay, this runs the code, which depends upon the add one crate. Depending on external crate in a workspace. We've already done that, right? Notice that the workspace has only one cargo.lock file at the top level of the workspace, rather than having a cargo.lock in each crate's directory. This ensures that all crates are using the same version of all dependencies. If we add the rand crate to the adder cargo.toml and add one cargo.toml files, cargo will resolve both of those to one version of rand and record that in the one cargo.lock. Making all crates in a workspace use the same dependencies means the crates in a workspace will always be compatible with each other. Let's add the rand crate to the dependencies section in the add one cargo.toml file to be able to use the rand crate in the add one crate. So in add one cargo, we're going to do rand equals, and then they just happen to memorize this, but let's go make sure that that's what we want to do. I think it's creates, yeah, creates IO. We have rand here. Yeah, so 053. So I want to add this to, did they say add one where we're adding this? Yeah, add one. So in add one cargo.toml, in the dependencies, we're adding rand equals and whatever its latest version is. We can now add extern crate rand to the add one source librs file, and building the whole workspace by running cargo build in the add directory will bring in and compile the rand crate. So extern crate rand in add one source librs extern create rand, and when we rebuild, blocking, waiting for file lock on the registry index, so it knows that thing has changed, and it has to now like download and sort of like set everything up. And the next time we do this, it shouldn't have to download rand again, because it will notice, oh, I still have you. The lock file matches. We don't need to re-download. All right, so continuing. The top level cargo.lock now contains information about the dependencies of add1 on rand. However, even though rand is used somewhere in the workspace, we can't use it in other crates in the workspace unless we add rand to their cargo.toml files as well. For example, if we add extern crate rand to the adder source main rs file for adder crate, we'll get an error. And it's because, so it can't find it because we need to add it to that cargo.toml. Interesting, error, use of unstable library feature rand. Use rand from crates.io. So it really wants me to use that one. Let's go ahead and run that just to make sure that that's really what's happening. So we have extern create add1, and we want extern create rand. We'll build this again, and use of unstable library, Rust C private. So it's a slightly different message than they sort of shared with us from the book, but it's basically the same exact outcome, which is don't do that. Get the one from, like, put it into your dependencies. To fix this, edit the cargo.toml file for the adder crate and indicate that rand is a dependency for that crate as well. Building the adder crate will add rand to the list of dependencies for adder in cargo lock, but no additional copies of rand will be downloaded. Cargo has ensured that every crate in the workspace using the rand crate will be using the same version. Using the same version of rand across the workspace saves space because we won't have multiple copies, and ensures that the crates in the workspace will be compatible with each other. But it's of course the opposite too, right? Because if we decide that we do need a newer version in like one area, we can slowly update those and not be forced to have to do massive refactors before we're ready for them. Adding a test to a workspace. For another enhancement, let's add a test of the add1 function within the add1 crate. I mean, there's kind of a test there, but I guess we can do a real test. So inside of here, we have config tests, mod tests, super r, and our test, adds 1. And then we can do assert equal, and we can say, okay, add 1 and pass it in like 5 equals 6. Okay. Now run cargo test in the top level add directory. That cargo test. Oh, I need to fix the code problem that I ran into. So in main rs, I want to just remove that line, and now we should be able to run cargo test. Running one test, test, add 1, adds 1, okay. And this is compiling adder. I wonder if it would go through and like do a separate one, or if these would all be the same one, but I suspect that we're about to find that out in the book. The first section of the output shows that the it works test in the add1 crate passed. The next section shows that 0 tests were found in the adder crate. And then the last section shows 0 documentations were found in the add1 crate. Running cargo test in a workspace structured like this will run the test for all the crates in a workspace. We can also run tests for one particular crate in a workspace from the top level directory by using a -p flag and specifying the name of the crate we want to test. So same exact thing as cargo run. This output shows cargo test only ran the test for the add1 crate and didn't run the adder crate tests. If you publish the crates in the workspace to crates.io, each crate in the workspace will need to be published separately. The cargo publish command does not have a --all flag or a -p flag, so you must change to each crate's directory and run cargo publish on each crate in the workspace to publish the crates. For additional practice, add an add2 crate to this workspace in a similar way as the add1 crate. As your project grows, consider using a workspace. It's easier to understand smaller individual components than one big blob of code. Furthermore, keeping the crates in a workspace can make coordination between them easier if they are often changed at the same time. Okay, so if we wanted to add one more, we can add like an add2 to this. So we'll do cargo new --lib add2. So then it's telling us we need to now come in here to the cargo.toml file and add in add2. But we also need to go in to the main, let's see, toml in adder and put in this exact same thing here, which is add2 equals path equals add2. And then finally in main rs, we can do extern crate add2. And so then we have num, we have original number is this, add1, and now we can basically just recreate this one. Which is original number is blah after adding 2. 1 is, and this is going to be add2. Now, of course, the problem is I haven't actually done that yet. So let's go into add2. We have the, just go to lib add2 source. Here we go. Pub function add2. This also takes in x, which is an i32. It's going to return an i2, and it just returns x plus 2. Super, super simple. Let's go ahead and run this and see how it goes. Well, actually, we need to build it first. So cargo build, and then cargo run -p adder, and the original number is 10. After adding 2 is 12. So perfect. Next section. Installing binaries from crates.io. Drop frames 125. So don't know when that, I don't know if that happened right at the beginning or if it's continuing on, but keep an eye on it. Installing binaries from crates.io with cargo install. The cargo install command allows you to install and use binary crates locally. This isn't intended to replace system packages. It's meant to be a convenient way for Rust developers to install tools that others have shared on crates.io. Note that you can only install packages that have binary targets. A binary target is the runnable program that is created if the crate has a source main.rs file, or if another file is specified as a binary, as opposed to a library target that isn't runnable on its own, but is suitable for including within other programs. Usually, crates have information in the README file about whether a crate is a library, has a binary target, or both. All binaries installed with cargo install are stored in the installation roots bin folder. If you installed Rust using rustup and don't have any custom configurations, this directory will be home cargo bin. Ensure that directory is in your path to be able to run programs you've installed with cargo install. For example, in chapter 12, we mentioned that there's a Rust implementation of the grep tool called ripgrep for searching files. If we wanted to install ripgrep, we could run the following: cargo install ripgrep. So let's actually, I don't know if I did that. Ripgrep. So let's do that. So cargo install ripgrep. It feels interesting. Well, I guess, okay, so it downloaded ripgrep first, and then it downloaded all of the dependencies for that. Is it compiling these in reverse order? No, because like void is in the middle here, and it compiled void first. So I don't really know what the order is. Also, it downloaded and then installed ripgrep right away, and then downloaded all of the supporting libraries, which feels a little bit odd. Like, I would think that the install should happen last for the actual thing. But let's go ahead and wait for this to finish downloading and installing. Although we could continue reading as we're waiting. Okay, so we've got this downloading. The last line of the output shows the location and the name of the installed binary, which in the case of ripgrep is RG. As long as the installation directory is in your path, as mentioned previously, you could then run rg-help and start using a faster, rustier tool for searching files. Oh, so this is such a nice feature. So few install tools actually tell you where they're installing at. Ah, this is taking forever though. So we'll just continue on. Extending cargo with custom commands. Cargo is designed so you can extend it with new subcommands without having to modify cargo. If a binary in your path is named cargo something, you could run it as if it was a cargo subcommand by running cargo something. Cargo is designed so you can extend it with new interesting, so subcommands. Custom commands like this are also listed when you run cargo -- list. Being able to use cargo install to install extensions and then run them just like the built-in cargo tools is super convenient benefit of cargo's design. Okay, so if a binary in your path is named cargo something, so it has to be named cargo -- you could run it as if it was a sub command. So maybe some kind of like build tool or something else like automate some things. It's still compiling stuff. Summary. Sharing code with cargo and crates.io is part of what makes the Rust ecosystem useful for many different tasks. Rust's standard library is small and stable, but crates are easy to share, use, and improve on a timeline different from that of the language. Don't be shy about sharing code that's useful to you on crates.io. It's likely that it'll be useful to someone else as well. But that's the end of chapter 14. So that moves us on to chapter 15, smart pointers. No further lost frames, and aha. So we finished this. Let's see if we can use it. So installed. Oh, interesting. Installed into home Brooks cargo bin RG. All right, so if we just do RG -B, hey, so it's in my path already. So if I wanted to search for like add, I guess we could just do RG pattern and then the path. So maybe add, and then the path would be like dot. And yep, and here's all the files with it. That'll be something to sort of think about and potentially use. In the meantime, let's prepare ourselves for chapter 15. Close U. CD out of here. Take chapter 15. All right, we don't know what to do yet, but that'll be coming up very shortly. Smart pointers. A pointer is a general concept for a variable that contains an address in memory. This address refers to or points at some other data. The most common kind of pointer in Rust is a reference, which you learned about in chapter 4. References are indicated by the ampersand symbol and borrow the value they point to. They don't have any special capabilities other than referring to data. Also, they don't have any overhead and are the kind of pointer we use most often. Smart pointers, on the other hand, are data structures that not only act like a pointer, but also have additional metadata and capabilities. The concept of smart pointers isn't unique to Rust. Smart pointers originated in C++ and exist in other languages as well. In Rust, the different smart pointers defined in the standard library provide functionality beyond that provided by references. One example that we'll explore in this chapter is the reference counting smart pointer type. This pointer enables you to have multiple owners of data by keeping track of the number of owners and, when no owners remain, cleaning up the data. Okay, so it can have multiple functions can take ownership of it. Is that what the smart pointer does? In Rust, which uses the concept of ownership and borrowing, an additional difference between references and smart pointers is that references are pointers that only borrow data. In contrast, in many cases, smart pointers own the data they point to. We've already encountered a few smart pointers in this book, such as string and vect in chapter 8. Although we didn't call them smart pointers at the time, both these types count as smart pointers because they own some memory and allow you to manipulate it. They also have metadata, such as their capacity, and extra capabilities or guarantees, such as with string ensuring its data will always be valid UTF-8. Smart pointers are usually implemented using structs. The characteristic that distinguishes a smart pointer from an ordinary struct is that smart pointers implement the deref and drop traits. The deref trait allows an instance of the smart pointer struct to behave like a reference, so you can write code that works with either references or smart pointers. The drop trait allows you to customize the code that is run when an instance of the smart pointer goes out of scope. In this chapter, we'll discuss both traits and demonstrate why they're important to smart pointers. Given that the smart pointer pattern is a general design pattern used frequently in Rust, this chapter won't cover every existing smart pointer. Many libraries have their own smart pointer, and you can even write your own. We'll cover the most common smart pointers in the standard library. So There's box T for allocating values on the heap. RC, reference counting type that enables multiple ownership. And ref T and ref mute, access through ref cell, a type that enforces the borrowing rules at runtime instead of compile time. In addition, we'll cover the interior mutability pattern, where an immutable type exposes an API for mutating an interior value. We'll also discuss reference cycles, how they can leak memory, and how to prevent them. Let's dive in. Using box T to point to data on the heap. The most straightforward smart pointer is a box, whose type is written box T. Boxes allow you to store data on the heap rather than on the stack. What remains on the stack is the pointer to the heap data. Refer to Chapter 4 to review the difference between the stack and boxes don't have performance overhead, other than storing their data on the heap instead of on the stack. But they don't have many extra capabilities either. You'll use them most often in these situations. When you have a type whose size can't be known at compile time, and you want to use a value of that type in a context that requires an exact size. When you have a large amount of data and you want to transfer ownership but ensure the data won't be copied when you do so. When you want to own a value and you only care that it's a type that implements a particular trait rather than being of a specific type. We'll demonstrate the first situation in the Enabling Recursive Types with Boxes section. In the second case, transferring ownership of a large amount of data can take a long time because the data is copied around on the stack. To improve performance in a situation, we can store the large amount of data on the heap in a box. Then, only the small amount of pointer data is copied around on the stack, while the data it references stays in one place on the heap. The third case is known as a trait object, and Chapter 17 devotes an entire section using trait objects that allows for values of different types, just to look at that topic. So what you learn here, you'll apply again in Chapter 17. Using a box T to store data on the heap. Before we discuss this use case for box T, we'll cover the syntax and how to interact with values stored within a box T. Listing 15.1 shows how to use a box to store an i32 value on the heap. File name, function main, let b equals box new, and pass it in, like, just in this case, integer 5, print line b equals b. Interesting. Kind of want to try that. So we'll do boxes. Cargo new boxes. Go to boxes, open up code here. All right, so let box equals box new, and then we'll hand it 5. Print line content where the box is. Available update later. And then box. Now you seem to be upset here. Expected pattern found equal sign. So what did I do wrong? That b equals box new 5. That's exactly what I have, but it's upset about this. It's always right. Oh yeah, I just doubled the amount of frames that have been dropped. It's always right at 745. Oh yeah, okay. Let's save this and try running it because we have that squiggly line and that's not fun. Cargo run. Compiling boxes, expected pattern. Can I not use box? Is that a required name? B? Oh, that's what the problem is. I can't use like lowercase b box. But this works, the box is 5. We define the variable b to have the value of a box that points to the value 5, which is allocated on the heap. This program will print b equals 5 in this case, and we can access the data in the box similar to how we would if this data were on the stack. Just like any owned value, when a box goes out of scope, as b does at the end of main, it will be deallocated. The deallocation happens for the box stored on the stack, and the data it points to stored on the heap. Putting a single value on the heap isn't very useful, so you won't use boxes by themselves in this way very often. Having values like a single i32 on the stack, where they're stored by default, is more appropriate in the majority of situations. Let's look at a case where boxes allow us to define types that we wouldn't be allowed to if we didn't have boxes. Enabling recursive types with boxes. At compile time, Rust needs to know how much space a type takes up. One type whose size can't be known at compile time is a recursive type, where a value can have as part of itself another value of the same type. Because this nesting of values could theoretically continue infinitely, Rust doesn't know how much space a value of a recursive type needs. However, boxes have a known size, so by inserting a box in a recursive type definition, you can have recursive types. Let's explore the cons list, which is a data type common in functional programming languages, as an example of a recursive type. The cons list type we'll define is straightforward except for the recursion. Therefore, the concepts in the example we'll work with will be useful anytime you get into more complex situations involving recursive types. More information about the cons list. A cons list is a data structure that comes from the Lisp programming language and its dialects. In Lisp, the cons function, short for construct function, constructs a new pair from its 2 arguments, which usually are a single value and another pair. These pairs containing pairs form a list. The cons function concept has made its way into more general functional programming jargon. To cons x onto y informally means to construct a new container instance by putting the element x at the start of this new container, followed by the container y. Is that sort of like a linked list then? Each item in a cons list contains 2 elements, the value of the current item and the next item. The last item in the list contains only a value called nil without a next item. The cons list is produced by recursively calling the cons function. The canonical name to denote the base case of the recursion is nil. Note that this is not the same as the null or nil concept in Chapter 6, which is an invalid or absent value. Although functional programming languages use cons list frequently, the cons list isn't a commonly used data structure in Rust. Most of the time when you have a list of items in Rust, vect is a better choice to use. Other, more complex recursive data types are useful in various situations, but by starting with the cons list, we can explore how boxes let us define a recursive data type without much distraction. Listing 15.2 contains an enum definition for a cons list. Note that this code won't compile yet because the list type doesn't have a known size, which we'll demonstrate. Okay, so file name, we create an enum list that has cons, which is i32, and the list itself, and then nil. Okay, so enum list. And we're basically taking in cons, which exists. Well, we're sort of like creating this idea, aren't we? It takes in an I32 number and the list itself as a second thing, and of course, nil is the other option here. All right, what are you upset about? Recursive type list has infinite size. Recursive type has infinite size. Help. Insert indirection, e.g. a box, RC, or reference at some point to make list representable. So what we want to do, like this is a box type list, like that. Yeah, I think that's how it would be. Note we're implementing a cons list that only holds I32 values for the purpose of this example. We could have implemented it using generics, as we discussed in chapter 10, to define a cons list type that could store values of any type. Using the list type to store the list 1, 2, 3 would look like the code in listing 15.3. So let list equals cons 1, cons 2, cons 3, and nil. Okay, so we can set that up. I think we can sort of. It's kind of like erroring out, so we have to add in the box here. So we can do let list equals list. What type is it? List cons. Oh, it's just let list equals. Oh, interesting. Oh, use list cons nil. Interesting. I hadn't thought about that. So use list cons, and then they're also doing nil here. Okay, so then we're able to say let list equals cons, which is 1, but then we have to have another cons with 2, cons 3, and then nil. And then I guess we could print this line out. So list is, it's an enum, so we'll we don't have a debug in it, do we? So let's just ignore this right now. It's actually going to yell at us because we're not putting these into boxes, right? So we have to put, this one is fine. This one needs to go inside of a box. Okay, so we add that in here. And then cons 2, and that's fine, but now box needs to go in here. And then 3 is nil. That should be fine. What did I do wrong? Incorrect closed delimitator. Do I have too many? Not enough? No, I have no idea how many I'm supposed to have. I'm not going to worry about that right this second. The first cons value holds 1 and another list value. This list value is another cons value that holds 2 and another list value. This list value is one more cons value that holds 3 and a list value which is finally nil. The non-recursive variant that signals the end of the list. If we try to compile the code in listing 15.3, we get an error, which is recursive type infinite size. This error shows this type has infinite size. The reason is that we've defined list with a variant that is recursive. It holds another value of itself directly. As a result, Rust can't figure out how much space it needs to store a list value. Let's break down why we get this error a bit. First, let's look at how Rust decides how much space it needs to store a value of a non-recursive type. Okay, so we are going to be getting into that, but next time, because it is 7:56, it's time to wind down the stream and then go on about our day. So first of all, this is just not working. So I'm just going to remove it because it is very, very unhappy. But we sort of have the beginnings of our entire cons list sitting here. Let's go ahead and close you out. And we'll head over to Learning Run Base and open up code here so we can update where we're at. So in our README, also right here, we're going to be at, starting with next time, computing the size of a non-recursive type. So currently at here, and click on that. Here we go. And there's an update available again. Don't worry. I have been like installing these updates, but they keep on, there's so many updates that have been coming out. All right, so we have all of these installed and ready to go. Is there anything else that we care about? I think the big thing is like the documentation fixes for the book. I didn't put the URL for this. Let's go see if we can find that, because it was here. No, it was one further back. So cargo new bind, cargo new add one. This one specifically. So it's in this section. The documentation fixes for the book. This is the chapter 15. So we'll put that into there so that we can find it later again and potentially put in a pull request for that. Right now, though, we're getting ready for the end of the stream. So we have this updated. Let's go ahead and push up any changes we need. Just a whole bunch of stuff that we installed. Everything looks good. So we did finished chapter 14 on to 15 and smart pointers. And we'll push that on up. So I have that code listed in the stream description. Miguel couldn't participate today, but with the stream on the background, I still picked up some new stuff. Awesome. Well, I'm super happy that you're able to pick up some new stuff. Next week, we're going to continue in with these smart pointers and this cons list. I hadn't heard of a cons list before, just sort of like of the standard linked list. So that'll be super interesting to see how that works. Next week? No, tomorrow. Wait, today is Wednesday. Yeah, tomorrow's Thursday. I should be fine. So tomorrow morning at 7 a.m. Mountain Time, I'll be continuing and we'll be working with this. And I have the code up, links to the code in the description. Said no, next week. Yeah, well, sorry about that. I let myself get a little bit dyslexized there. That's not what I meant to say. So let's just pretend that I don't have a recording of me saying that. With that, I don't really have anything else. Just come watch, join the community, click the follow and subscribe buttons and all that normal stuff to get notifications when I go live. So we don't have to rely upon me remembering to put out the Twitter messages, which usually works, but sometimes doesn't. If only the internet recorded people and everything they ever said. Well, they do for an hour a day for me. Someone should invent that. I think those are the body cams. And I don't know if I want everybody to have one. That might be a little bit too much. But with that, I'm going to go on and get ready for the rest of my day. And I hope you all have a great rest of your day too. Thanks again for stopping by, and I'll see you tomorrow.